we are going to see more application of integral, particularly definite integral. Let's recall how we introduced the concept of definite integral. We started by considering area of region under graph of a function over interval a to b. The original idea was to slice the region into strips and estimate the area of each strip. So if we again just analyze one strip among n of them, then we would add areas of all those strips, call that the Riemann sum, and send it to infinity, then we get the area. But if you think about it, the area of each strip is approximately the height f of x times the width dx. So area of each strip is estimated by multiplying the height by the width. Then we add them up, like I said, have a Riemann sum, then we take a limit, sending into infinity, meaning we really slice the region into infinitely many strips, and we get total area. Now this whole idea is then showing by this integral notation. So this represents the sum, this stretched, this integral sign is like a stretched S sum starting from end A to end B. So this definite integral notation was introduced to really capture, to reflect what's really going on. So we end up with this definite integral. With that, we turn back to say, okay, this definite integral could represent the area. All right. So with a similar idea, we're going to see how to calculate the area between two curves. Say we have one above here. I actually call it as a YA above. We have another function with this blue graph. I call the YB as below. Okay. Then we, of course, slice the region into infinitely many parts, as we saw in the original, kind of setting. All we need to do is to try to estimate the area of this one strip, then add them up, obtain the Riemann sum, and send to into infinity, and get the area of this region, just like how we got the area of the region above here. Okay, so now this one strip again is approximately a rectangle. So we're going to have a height, we're going to have the same width. So the area is obviously, area of this little strip is obviously the height times the width. This time you look at the graph, the height is actually YA minus YB. So once you have the graph, you can see what's YA or what's YB. Then the area of this yellow shaded region will be the sum of dAs, the sum of these guys. From A to B. This is how we come up with a definite integral for area of the region between two curves. So the key is to come up with the YA minus YB times dx. Area of one strip, then add up and look at the graph to see where you can start value A to value B. All right. It's very important that you graph, because if you don't have a graph, you're not going to be able to see YA, YB, or anything. Okay. Now this is how we can do figure out area between region. Now, sometimes we have graphs that enclose region in a different way, like this. Suppose this region is enclosed by a graph here. For now, let me call it as x on the right side. This I'm going to call it as x on the left side. All right. So for this kind of region, we will not slice the region like how we do it usually in the vertical fashion. Reason is, if we try vertical slice, let's see. If we try vertical strip, okay, somewhere in the middle, right? Then the YA will be this line here at the location D, Y above, Y below. YA will be D, Y, let me write that. So YA will be D, YA will be D, YB below would be actually value C here, right? That's no problem. The problem is, if we move the strip to this side of the region, the YA will be different. YA will be here, which would be represented by some function, whatever that's going to be. So the issue is, it will be the high as YA minus YB will change. The YA will change, will be different. So we cannot have one expression for the height of strip. As a matter of fact, if you place your strip somewhere here, it's much more complicated. See, you're going to have two different sections, so it's just totally, it's impossible. So mathematically, the issue is, it's impossible to use simply one expression for the age to represent of the height of strip across region. What it means is, you would have to set up different integrals, because your YA could be different for some strips, YB could be different for some strips, right? Just complicated. So it's not, in this case, good idea to still choose vertical strip or slice the region vertically. All right, let's see. Let me draw the graph again. So basically, we have a situation like this. This is a C. This is a D. So cannot do vertical strip. So instead, we're going to pick up horizontal strip. The calculus concept is the same. We slice it, we can somehow figure out the area of one strip. Then add them up, have a Riemann sum, send the infinity, so on. We end up with the definite nickel, right? But we're going to do this time slice region horizontally. So since it's a horizontal strip, you can see the area would be approximately the length times the thickness. In this case, it would be dy. How thick it is? It would be dy. So length times dy. Make sense? Since it's a horizontal distance, the length is x value at this end, right end, minus x value at the left end. So we'll be looking for x value or expressions for x value. Once you have that, then add them up. Add all those areas of strips up from C to D. From the graph, you can see from C to D. Our strips would start from here. The first strip, second strip, third strip, going up all the way to D. Okay, so it's the same calculus concept. C to D. X right side minus x at the left dy. So the y is going to be a variable. Okay, horizontal strip, y is a variable. Back here, vertical strip, x is a variable. You have dx. Vertical strip, you have a dx. Horizontal strip, you have dy. You don't even have to memorize, because once you pick up the strip, just see what axis it would intersect with if you have to extend it. So with the horizontal strip, if you extend it in this case, it would intersect with the y-axis, so you know it's dy. Similarly, a vertical strip, if you extend it, it would hit x-axis, so it's dx. Sometimes you don't even have to extend. Like you have a, say, a region like this. You pick up a horizontal strip, if you choose to, it actually already intersected with y, so you know it's dy. On the other hand, the same region, if you put, say, similarly, you have a region like this, you pick up a vertical strip, it already intersected with the x-axis. What I'm saying is, if you have to extend it, let's see which axis it would cross, so you know it's dx or dy. All right, now let's see example. Now the handwriting is horrible because it's hard to control the stylus pen, but let me read. So find the area enclosed by the graphs of y equal to x squared minus 4 and y equal to 4 minus x squared. All right, so you have to look at the graph to even start to pick up strip. So this kind of problem, with no graph, there's no way you can do it. Right? So let's graph. First, we graph y equal to x squared minus 4. Let's use a different color. Y equal to x squared minus 4 looks like this. Y equal to 4 minus x squared. Looks like this. Okay, so the region, this is the region. Now, what strip to pick up? If you're not sure, you can always start with a vertical strip. Okay, start with the vertical strip. Now you can check whether it's going to work. It's going to be complicated. How you check is to visually imagine this strip moving across the region with the vertical strip. That's just a representative, right? In reality, you would have infinitely many strips. Okay, but imagine this strip moving across the region, seeing if the top or the bottom would jump from one curve to another. It's not going to happen. As we can see, no matter where the strip is, the top will always stay on the blue curve, which is represented by y equal to 4 minus x squared. And the bottom will always stay on the graph of the red one, y equal to x squared minus 4. This means we will be able to have one expression for the height of the strip throughout the region. So this is not going to create any problem or issue. Okay, so we'll just go ahead, say vertical strip. Vertical strip, the area is y above here, y below here. So it's ya minus yb dx. Remember, this strip actually intersect with the x-axis, so it's dx. With the specific, expressions for ya, yb, we can actually plug in. So it'd be x squared minus 4 minus, no wait, ya is 4 minus x squared. 4 minus x squared minus x squared minus 4, which is yb. So you simplify it, it is 8 minus 2x squared. All right, now our integral will be then a to b a minus 2x squared times dx. Now, from where to where? Well, it's not given, but we can tell from the graph. It's going to go from this value to this value, because this is where we're going to pick up our first strip, second strip, and move across and stop here. Okay, so we need to find the intersection of those two graphs. That it's simple algebraically. Just set the functions equal to each other. You can solve. It's 2x squared equal to 8x equal to plus or minus 2. So this location is negative 2. This location is positive 2. How we determine our limits in the integral. Okay, so most important thing is to set up a definite integral. Of course, you can easily simplify. In this case, just find the antiderivative, the capital F. So it'd be ax minus 2 over 3 x to the third power capital F. We will plug in 2, plug in negative 2, use a calculator. So a times 2 minus 2/3 times 2 to the third minus a times now negative 2 plug in 4x in capital F and simplify, get the area of the yellow shaded region. All right, so graph, let's see clearly the region close, then try strip. Start with the vertical strip, see if there's any complicity. Move it across, see if whether top or bottom would ever jump from one curve to another. If not, just go ahead. Okay, let's see another example. So this time we will try to find the area enclosed by the graphs of y equal to x minus 1 and y squared plus 2x plus y squared equal to 2x plus 6. Okay, of course always we start with the graphing. Y equal to x minus 1. Let me use different colors so we see better. Looks like this. Y squared equal to 2x plus 6. It's not very clear what it looks like, but let me rewrite. Let me solve for x. So it would be divided by 2 will be 1/2 y squared minus 3. Subtract 6, divide by 2. So I can see this is a parabola opening to the right. So I'm going to graph it. It will look like this. Now this is just a demonstration. I am not sure whether the two graphs will actually intersect on y-axis. All right. Let me actually probably just redraw, because I'm not sure where it's going to intersect. So let's draw like this. If needed, I can always make adjustment. Don't want to create any confusion or intersection that's misleading. Okay, so anyway, so this will be y squared equal to 2x plus 6. Graphing is very important, and this will be y equal to x minus 1. Now the region is clear. This is the region. Okay. Well, this time though, you can see it's not a good idea to use vertical strip, because let's have a vertical strip for now. The bottom of the strip would jump from the red one to the green one if you move it across from left to right, right to left. Because if it's here, the bottom is on the straight line. If your strip is here, the bottom is actually on the right, on the red curve. So that's not good. So we're not gonna use the vertical strip. Instead, we use a horizontal strip. Now, will this create any problem? Well, let's see. Vertical strip would go up and down to cover the whole region. So as we can imagine, no matter where we place a horizontal strip within the region, the left is always on the parabola, while the right end will always on the straight line, which means it's good, which means we only need to set up one integral for the area of the region. Okay, so we're going to stick to this horizontal strip. So again, try to figure out the area of one strip. That be length times dy, the thickness of the strip in the vertical direction, in the y direction, so it's dy. And the length, of course, is xr minus xl. xr, as we can see, the xr is on the straight line, represented by y equal to x squared. So we need to solve this for x. This way the equation will read as x equal to, you're looking for x, you have to solve for x. Once you solve it, then you have the expression, correct expression to plug in. Y plus 1, plug in for x. Okay, your x value is given by y plus 1. So y plus 1 plug in. XL is on the parabola, represented by this quadratic equation. So again, since we're looking for expression to plug in for x, we need to rewrite this equation in the form as a new one in the form of x equal to, all right, we actually, when we try to graph this, we already solved it. So I'm going to just copy the 1/2 y squared minus 3. Okay, so don't just plug in just because you find the equation here, just plug in without thinking 2x plus 6. You have to know what you're looking for. You're looking for x. You're looking for x, you have to solve for x. You solve for x, and this is what you're going to plug in for. For the XL, 1/2 y squared minus 3 dy. So you simplify it, it's negative 1/2 y squared plus y plus 4. There's a 1, there's a positive 3, so it's positive 4 together. And then again, we add them up, it'll be integral of this function from c to d. Now, c to d, what are they? Well, from the graph we can tell it's going to be some value here to some value here. So this is going to be our C, this is going to be our D. Because your black strip, if you think about it, right, would go from location C all the way up to D. Your horizontal strip here would start from here. Okay, what are they? Not given, not clear, but what's clear is these are intersections of the graphs. So we're going to solve. Okay. Now how we solve? We usually set x equal to x or y equal to y. I already have the parabola expressed as x equal to, so I'm going to use this one for the straight line. So set the x equal to x. 1/2 y squared minus 3 equal to y plus 1. All right, so simplify it. Maybe 1/2 y squared minus y minus 4 equal to 0, and multiply by 2. In factor, y minus 4y plus 2. And set each to 0, and then you can see c equal to -2, d equal to +4. You just set each to 0. Set this to 0, set this to 0. You find the y equal to 4 and the y equal to -2. From the graph, we can tell this must be -2, this must be +4. So the -2 to +4. Then find that the rest is just simple integration. You find the antiderivative. Let's see. So it will be -3 1/6 y to the third power 1/2, simple integration. And then plug in 4 for y and -4y to finish it up. The most important thing is to set up the definite integral correctly. Okay. All right, so this is how we evaluate area of the region between two curves. Let's stop here.